Imagine a network that doesn't just react to your signal, it anticipates it. A tower that knows you're about to stream a movie before your phone even opens the app. A beam that shifts before you walk into a hallway, avoiding a dead zone. A system that learns from your habits, the weather, the crowd density, all in real time, and adjusts without a single command. This isn't science fiction. It's the next evolution of wireless, powered by foundation models, the AI revolution that's turning networks from passive data pipes into intelligent, reasoning systems. So what is a foundation model? Think of it as a universal AI brain, trained on vast, diverse datasets across language, vision, audio, and now, radio signals. Unlike older AI models built for one narrow task, like face recognition or traffic prediction, FMs learn general patterns, common sense, and even causal reasoning. They understand context. They infer intent. They think. And now researchers are teaching these models to understand wireless networks, not as static systems, but as dynamic, evolving environments shaped by movement, interference, and human behavior. The real breakthrough: multi-modal data fusion. For decades, networks operated on siloed information, signal-to-noise ratios, traffic volume, cell load. But today's devices are sensor-rich: smartphones with cameras, LiDAR accelerometers. Base stations collect video from street cameras, radar from drones, GPS from vehicles. Foundation models don't just process this data, they understand it. They see a car approaching a building, not just as a moving object but as a potential signal blocker. They correlate a sudden drop in signal strength with a bus turning a corner, not just a random fluctuation. This is intelligence, not prediction. Perception. Take beamforming, the process of focusing a high-frequency wireless signal like a laser. In 5G and 6G, these beams are incredibly narrow. But if a person walks in front of one, the connection drops fast. Now imagine an AI that uses camera data and LiDAR to see the obstruction before it happens. It doesn't wait for signal loss. It predicts the blockage, reconfigures the beam, and maintains the link in milliseconds. One real-world test using a 6G testbed with LiDAR data achieved 95% accuracy in beam prediction, with 90% less overhead than traditional methods. That's not just efficiency. That's proactive intelligence. So how does this work in practice? We break it down into two superpowers: prediction and control. First, prediction. Foundation models don't just analyze past traffic. They understand context. Was it raining? Was it rush hour? Was a delivery truck just parked in front of a cell site? A model called TrafficLLM uses few-shot prompting, a technique where it learns from just one or two examples to predict congestion without being retrained. It's like teaching a student with a single case study, not a full textbook. And for channel state prediction, critical for maintaining signal quality, researchers are turning raw radio signals into visual images. Yes, images. They map signal strength, phase, and interference into pixel-like grids. Then they feed them into vision-based AI models, like those trained on ImageNet. It's a clever hack. A powerful vision model can now see a radio channel. And it can detect subtle anomalies, like a sudden interference spike, before it degrades performance. Now the real magic: control. Prediction is powerful, but action is transformative. Here's how it works. Foundation models act as teachers for reinforcement learning agents, AI agents that learn by trial and error. But instead of letting them crash the network during exploration, the FM provides reasoning-guided supervision. It says, if you're in a high-traffic area, steer users toward underutilized beams. Avoid cell sector 3, its power is dropping. This is task planning with reasoning. The FM breaks down a complex goal, like maximize throughput, into a sequence of actions: traffic steering, beamforming optimization, power allocation, spectrum sharing. And it doesn't stop there. These models are becoming interactive agents, capable of understanding natural language commands. Imagine saying, "My video call is lagging, fix it." The AI doesn't guess. It analyzes your device's signal, checks your location, detects if a beam is blocked by a drone, and reconfigures the network in seconds. This isn't automation. It's agentic intelligence, AI that understands, plans, and acts. But here's the catch: foundation models are huge. Billions of parameters. Terabytes of memory. You can't run Llama 3 on a smartphone or a drone. So how do we make them work in real networks? The answer is smart deployment, a hybrid architecture built on three principles: privacy, speed, and scalability. Cloud for heavy-duty tasks, batch processing, model training, global optimization. Edge for low-latency decisions, beam tracking, real-time handovers, anomaly detection. On-device for privacy, processing sensitive data like your location or voice right on your phone. And collaborative inference, where your phone, a nearby server, and the cloud split the workload like a distributed brain. To make this efficient, we use model compression techniques. Quantization, reducing precision from 32-bit floats to 8-bit integers, cutting memory use by 75%. Pruning, removing redundant neurons, stripping away 50% of the model without losing accuracy. Prompt tuning, instead of retraining the whole model, we fine-tune just a few parameters, like adjusting a dial. With these tools, researchers have successfully run 10 billion parameter models on devices with just 4 GB of RAM. a feat once thought impossible. But challenges remain. We need better data. Real-world, multimodal datasets from 6G testbeds like DeepSense 6G and M3SC. We need methods to train on raw, unlabeled signals, because labeling channel measurements is expensive and time-consuming. Enter self-supervised learning, training models to predict missing parts of signals, like filling in a scrambled radio waveform, without human labels. And privacy. That's non-negotiable. So we use federated learning. Each device trains a local model on its own data, then shares only model updates, not raw data. It's like a global AI team learning together, without revealing their secrets. And to prevent hallucinations, when the AI makes up fake signal paths or predicts interference where none exists, we add guardrails. Constraint-based training, forcing the model to obey physical laws like signal propagation limits. Retrieval-augmented generation, RAG. Before making a decision, the AI pulls from trusted databases, like known channel models or historical outage records. Hybrid reasoning, combining symbolic logic with neural prediction, so the AI doesn't just guess, it reasons. And finally, what about smaller models? Because not every task needs a billion-parameter giant. Enter on-device small-scale foundation models, efficient, lightweight AIs trained using knowledge distillation, low-rank factorization, and pruning. They're fast, they're private, they're energy efficient. When combined with adaptive split inference, where the model dynamically decides whether to run locally or in the cloud, they become the perfect balance, local intelligence with cloud power on demand. This isn't just about faster speeds or lower latency. It's about building intelligent systems that understand the world, the way humans do. Systems that learn from movement, anticipate change, and act with purpose. The future of wireless isn't just faster. It's smarter. It's autonomous. It's adaptive. It's self-optimizing. And at the heart of it all, foundation models, not as tools but as co-creators of the network. The revolution isn't coming. It's already here. And it's not just managing signals. It's managing life. From your phone to your car, from the city to the stars, wireless networks are becoming intelligent ecosystems, shaped by AI that thinks, learns, and acts. The future of wireless isn't just digital. It's cognitive.